Welcome. This is Nathan Weezy, professor at Marquette University. This is Digital Control Power Electronics. In this section, we're going to talk about the voltage mode control of a boost converter. In black here, you can see that we have the topology of a traditional boost converter, and in blue, wrapped around it, we have the traditional structure of a voltage mode controller. Traditionally, we measure the output voltage in this structure, we compare it with a reference, and we subtract the two and we generate an error. That error will be fed into the controller, which we are going to design in this section. That controller will essentially output a duty cycle signal, which will be compared against a ramp, and an appropriate switching signal Q will be generated for the switching signal. In terms of what's going on with the ramp is kind of a constant increasing ramp that repeats every TS, and being compared against the ramp is the output of the controller. That will be D, and of course the comparison of those two will generate our switching signal Q. So whenever D is greater than the ramp, it'll be a 1, and vice versa. When it's not, it'll be 0. And here's how we generate our PWM. This is going to repeat again every cycle TS. Essentially, the frequency of this ramp here will set up the switching frequency. Okay, so we're going to design a voltage mode controller for this. So what we have set up here in our MATLAB script are a bunch of the converter parameters. So in this example here, we're going to boost from 5 volts to 10 volts, which is essentially a duty cycle of 0.5. We'll have 100 microhenry for our inductance, which is here. Capacitance of 247 microfarad, an ESR of 10 milliohms. Our max output power will be 10 watts, which will be 1 amp at 10 volts. We'll do 200 kilohertz for switching frequency, and of course, based upon our output power here, we can calculate the load resistance at that, which is going to be, in this case, just 10 ohms. Now, what we're going to do here is, for this next part, is set up the plant transfer function. Now, this is generally derived in an introduction to power electronics types course. Here we're just going to work with the result of it and design our controller based on that. So this is our plant transfer function. It depends on duty cycle. This is much different than the buck, so we actually have some stuff that moves around quite a bit. We have a right-hand plane 0 in the buck converter, and we'll talk about what that means. But we have this first thing we calculate is the effective inductance, and it's a function of the inductance and the duty cycle. That gets plugged into equation or line 20, which is the plant transfer function defined. You can find this in any traditional power electronics textbook. And what we'll go ahead and do is Bode plot this so we can take a look at what the transfer function looks like on the Bode plot. In terms of controller design, this is going to be very similar to what we've done for the buck. With voltage mode, we will have our controller design parameters here. And what these will do are set the gain and phase of our controller. And so we can set a bandwidth and we can set a phase margin. And bandwidth is going to essentially tell us, is very strongly correlated with damping, and gain or crossover frequency is very strongly correlated with response time and speed of the system. So what we'll go ahead and do is we will calculate the gain and phase of the plant at the desired crossover frequency. So this is that one point, that one crossover frequency. This is the plant, and we're asking for the gain and phase at that point. Once we do that in this design, what we'll go ahead and do is calculate phi boost. Phi boost is how much phase boost we'll ask from the controller at that point. The controller type will be a double pole double zero with an integrator, so K boost will give us our ratio between the pole and the 0. Line 37 is how much the controller gain we need in order to cross over a gain of 0 dB or gain of 1 at the desired crossover frequency. And once we have that, then we essentially can get the controller gains, which is these lines. And then what I've done down here is just define the controller transfer function based upon the integrator gain, the pole, and the 0. Essentially, this is what we get right here. Okay, so we can pull that out and take a look at that. These are where the pole and the zeros end up. We have a pole at 37,000 radians, a zero at 1,000 radians, and a gain of about 24. All right, so let's take a look at these transfer functions and see if we can make any sense of what's going on. If you take a look at our plant here, this is the plant in blue. In fact, let me go ahead and just outline this here. This is our plant, and you can see that we have a kind of an undamped complex pole there, complex pole pair. Our controller, which is actually shown here in red, let's see if we can show that here. This is our controller. And of course, you multiply the two. We designed this for, what do we design this across over for? 1 kilohertz here. We should have a gain. You should be able to see visually a gain of 1 or 0 dB at 1 kilohertz. So here's 1 kilohertz. If we look at the controller, we look at this, you can see these are both equal and opposite in sign in dB, right? So they ought to force the open loop to cross over at that point, which you can see here kind of in this orangish yellow. That is the open loop transfer function. So you can see it does indeed cross over through 0 right here, 0 dB. So our controller is designed properly. Let's just point out where the poles and zeros are here. This should be our 0 location, which was somewhere, what do we say, 1,000 radians. You can see that there. And this is approximately the pole location. You can see where the humps are essentially on our controller transfer function to locate those visually. Now, if we go ahead and close the loop, when we do GCL, you'll see what we have here in purple. We actually come down and we go down a little bit and come up and go down. So this is interesting because the boost is actually a pretty challenging converter to actually try to stabilize, and a lot of that's got to do with the right hand plane 0. So actually, let me go up here to the definition of the transfer function. Here, up here, you see this. This is actually a right hand plane 0. This is up in the numerator, and so what this does is add a little bit of complexity to the design process. So we have another 0. This is the ESR 0. You can see because you have the small r here, and then you have a complex pole pair. And so what a right-hand plane 0 is going to do is, so whenever you have some air in your system and you push on it harder, like for instance in the context of a boost converter, let's say your voltage is dipping, right, and you're going to increase the duty cycle in order to essentially bring the output voltage back up. It has the negative effect at the beginning, which is absolutely bizarre to think about. So you increase your duty cycle, get your voltage up, it actually dips more on you, and then after a little bit of a delay it'll start to come up, and that's essentially what a right hand plane 0 does in terms of the plant. So that can make the design of the controller much more challenging. All right, I think we designed for a phase of about 60 degrees. Let's see if we meet that in our open loop response. So if we look at that, remember this is from 180, so where's GOL? We got it here in orange. You can see that, where are we here? It should be about here, which looks about to be 60 degrees. Now this looks a little goofy because how MATLAB spit out the results for this, but this is indeed a phase margin of 60 degrees. It's just due to the way that MATLAB wrapped the phase on this when we plotted it out. So let's take a look now at a response for this transfer function and this controller. This is in continuous time. You can see what happens here is we have a transient from 10% to 100% load. And what happens here is our output voltage initially dips down and then starts to come up, overshoots a little bit and settles down. In this case, we settled down, and where we have this in seconds, you can see it's about 1 millisecond approximately, so 0.1 to 0.101. It's about 1 millisecond approximately, but just to give you some idea on what the bandwidth is actually doing, if you want this to be shorter, of course, you need to speed up your system. And of course, you overshoot a little bit here. Now, again, this isn't the best design because I'm just arbitrarily picking this frequency right now and this phase margin. So I just arbitrarily picked 1 kilohertz and 60 degrees. May not be the best for this application, just because you can look at the end design of the Bode plot, and actually you have this kind of dip. Sorry, I'm looking at phase here. You have this dip. You have a gain of 1 here, or 0 dB, and then you dip down and kind of come up over again and then down. You'd like to get that nice and flat, so what you would probably like to do better off is work on damping GOL right here, if you could a little bit. Do something with this. That will help quite a bit. You can also relax the constraint on the K-factor approach, so you don't have to put both zeros and both poles at the same location. That's what the K-factor approach does here, so you'd have a double pole, double zero, but you don't have to do that. You could manually start placing them, or you could look at lowering the frequency using the K-factor or increasing the frequency and see if you get better responses and better loop shaping of your open loop transfer function. All right, so actually I'm going to illustrate here too how when you push on the duty cycle right away you get this negative effect. So the voltage starts dipping here and you start pushing on it here, D, and guess what? It keeps actually going down, which is really, really interesting here. This is kind of that right hand plane 0. So all of a sudden your duty cycle is like, oh, I need to go back the other way because that's not working, right? And even here you can see that if this didn't have a right hand plane 0 and you were still going down, your duty cycle would actually keep going up. So this is actually quite a very interesting case. And a boost converter, again, is a pretty challenging converter to actually stabilize due to this right hand plane 0. And you really have to have a good understanding of what it's doing and how to effectively make your controller not overact to that, or essentially be stable in the sense of having a right hand plane 0. All right, thank you. This concludes this section on a voltage mode controller design for a boost converter. Thank you.